What's up, bitches? Today we're going to learn the first chapter of heat transfer. So your first chapter, it's just basic concepts. There's three equations that you have to know. First, it's heat transfer through conduction, heat transfer through convection, and then heat transfer through radiation. Super easy, okay? Basically, these are the three types of where heat can be transferred, okay? I'm going to explain to them one by one, but basically in your questions, you usually have Q total, which is equal to Q from conduction plus Q convection plus Q radiation. Okay. Now, some questions might not incorporate all three of these types, but this is the four basic equations that you have to know. These three are basically this is just easy shit. These three types of heat transfer is what you really have to understand for this chapter. Okay, so for conduction, it's basically where there's heat being transferred through a solid body. Okay, for example, let's take a wall, your house wall. Okay, outside it's gonna be very sunny, right? There's gonna be heat. Heat is gonna touch your wall, and that heat is gonna travel through your wall at the end inside of your house. Okay, so Q conduction over here is basically how much it's being that heat is being transferred. It's in watts. Negative K is your thermal conductivity. In your problem statements, whenever they mention thermal conductivity, your brain should directly go to this equation. A is the area where the heat source is touching, okay? So in this case, it's the area of your wall. Delta T over delta X is the hardest part to understand. Basically, it's just saying like how the heat changes through the body, okay? So usually for your first few chapters, it's just going to be equal to T2 negative T1 over X. Now, what the fuck is T1, T2, whatever? T1 is where the heat source is initially touching over here. So in this example, in your wall, it's going to be the outside wall where the sun is touching. T2 is where the heat is traveling towards, okay? So it's traveling towards the wall inside of your house. So that would be T2 over here. And what's X? It's the thickness of your wall, okay? Whoa. X. So to calculate delta T over delta X, you take T2, negative T1, divide the whole thing by the thickness of your wall. It's basically the slope of how the temperature changes through the body. That's it. It's really simple. Next, for your convection, it's basically a body that's being cooled through a liquid or air, okay? So if you take your cube, like a random cube, for example, and you just dunk it in water, okay? And the water is cooling down your cube, that's convection. Or if you put it in air, that would be convection, okay? So Q convection, again, it's in watts. H is your thermal coefficient. In your problem statement, whenever it says thermal coefficient, it's convection. AS is the surface area where it's touching, okay? So for example, this cube, if we put it on the floor, the surface area would be this, the top, and behind, okay? Not the bottom. You don't include the bottom. Some questions they do trick questions. AS is the surface area where the convection is happening, where the heat is being transferred to, okay? So for example, if you take a guy that's hot and you put them in underwater and he's being cooled in the water, the surface area is all of the outside area of that body, okay? TS is the surface's temperature. So if we take this cube that it's being cooled in water, TS is the surface temperature of that cube. T infinity is going to be the fluid's temperature. So for example, the water's temperature or the air's temperature. That's it. That's Q convection. Super easy. Okay, last thing, Q radiation is when you have a cube and he's emitting radiation or absorbing radiation, okay? In your problem statements, whenever they say emissivity or they mention that in your problem statement, your mind should go to Q radiation, okay? So again, Q radiation, this is in watts. This epsilon is your emissivity. It's going to be between 0 and 1. It's basically saying how much your body is absorbing radiation, okay? Next, sigma is just a constant. I think it's a Boltz's constant, some shit like that. I don't know what it's called, but it's just this. It's just a constant. It's nothing. As, again, is just your surface area where the body is absorbing radiation. TS, same thing. It's a surface temperature of your body, TS. Now, T surrounding is different. Since you're dealing with radiation, you don't really give a fuck about the air or the water. Usually it's going to be, for example, in a room, T surrounding is going to be the temperature of those surrounding objects. So for example, the temperature of the walls, that's going to be T surrounding, okay? Now, for the two other heat transfers, for the temperatures, you could just pick degrees Celsius or Kelvin. It doesn't really matter because you're just taking the difference. But here, it's to the power of 4. So the units do matter. You have to take Kelvin to solve this equation, okay? And that's it, super easy. All right, so for our first example, we're just going to cover a basic conduction problem. It's giving us an aluminum pan, blah, blah, blah. I'm not going to read the whole thing, but wherever you see thermal conductivity, the first thing that you do is you write your conduction equation. That way, you're already going to get partial credits. Negative K times A delta T over delta X. So the question is giving us the diameter of the pan, the thickness, the rate, and one of the temperatures. And it's asking us determine the temperature of the outer surface of the bottom of the pan. Okay, so usually for heat transfer, what I always do is I draw it just so it's easier to see. So you have your fire, and then you have your pan. And I guess you have water in it, whatever. All right. So for Q conduction, it's already given 800 watts. Negative K thermal conductivity, it's over here, 237. 237 times the area where, when it says A over here, it's basically talking about which area, like which surface is touching the fire or touching the heat, basically. So in this case, since it's a diameter, it's pi over 4 times diameter squared, 0.15 cubed. 0.15 because you have to take in meters. Now, delta T and delta X, what is this? Like I said, your first few chapters, delta T over delta X is just T2 negative T1 over X. It's just the slope on how the temperature is fluctuating in the body, okay? So, which one's T1, which one's T2? T1 is where the heat is first touching, and T2 is towards where the heat is traveling to, T2, right? So when you put your pan on the fire at the bottom, that's going to be T1. That's the first surface where the fire is touching. And then it's traveling all across the body of your pan up into T2, okay? So the X is going to be your thickness, which was, 0.4 centimeters. That's it, okay? So all we have to do is plug in the equations. It's already giving us the inner surface of the bottom of the pan is 105. So that's our T1. It's asking us the outer surface of the pan. So that's T2. So we're looking for T2, negative 105 degrees Celsius, divided by the thickness. And again, you have to take into meters. And the rest is just algebra. Solving all of this, you're going to get a T2 of about 105.76 degrees Celsius. That's it. The hardest part, honestly, is just this part over here, delta T over delta X. Once you understand how this works and what it actually means, it's super easy, okay? Again, it's where heat is touching a surface. For example, here, T1 is going to be the first part where the heat is touching. And then this body is going to have a certain thickness. T1 delta T over delta X is how much the temperature is changing. X. That's it. All right, let's do a last problem. This one's a little bit harder. It's basically giving you a person standing in a room, blah, blah, blah. I'm not going to read the whole thing, but basically, you're dealing with radiation and convection, okay? So in this case, Q total is equal to Q conduction plus Q convection plus Q radiation. In this question, they're not mentioning any Q conduction, so we're just going to assume this is equal to 0, okay? So the Q total is equal, look, when you read the question and you see that the, where is it? Over here, heat transfer coefficient, automatically your brain should go convection. And then when you get an emissivity, your brain should go to radiation. Since we have both of these, Q total is equal to Q convection plus Q radiation, okay? So I'm just going to write out the equations. H times S times T, what was it? S negative T infinity plus the equation for the radiation. Emissivity, sigma, S, TS4, negative T surrounding 4. All right. So the question is just asking us What's it asking us? Determine the total rate. Okay, so we're just finding Q total. So we have H, it's given over here, the heat transfer coefficient, 5. As, the area is given over here. Where is it? Exposed temperature, skin temperature, the person is 1.7. 1.7. The surface would be 32 over here. That's what it says. Negative the surrounding area, 23. Plus your emissivity, 0.9. Times this constant, 5.67 times 10 to the power of negative 8. Times as, 1.7. T surface, which was 32, right? However, over here, you're just taking the difference. So it doesn't matter if you're doing a Celsius or in Kelvin, it's going to be the same thing. But since here it's the power 4, it does matter. It has to be in Kelvin, okay? Plus 273 to the power 4. Minus. Now, usually T surrounding, you would be taking the temperature of like the room, walls, or the floor, something like that. But in this specific question, it's telling you to just assume where the surfaces of the room is the same as air temperature, which was 23. So I'm just going to write 23. 273. The power 4. That's it. The rest is just you grab your calculator and you calculate everything. And doing this properly, you should get a Q total of about 161.26 watts. That's it. Easy peasy.